Okay, so how is going? So far, so good? Yeah. Okay. Who's going to give us a little recap of the introductory part? Oh, everybody's like this right now. Yeah, no, not me, please. Come on. You want? I don't remember your name. Enrico, come on. The first part, what we did. Wait. You want to turn on? Okay. Yeah. I was all shining, sorry.
We had an introductive example to Bayesian networks. So then you go through a bit of graph terminology, introduce a couple of structures like the moralities and the V structure and the common cause, and then we see the Bayesian network factorization.
Okay, good, Enrico. Very good. Someone wants to add something? There was something else? What was important in the first part, in your opinion? When you had the coffee break, you thought, it's not true, of course, but let's assume that you thought about the course. So, I'm bringing with me this example, or I'm bringing with me this thing here that I wouldn't have thought about. Dimmi, no, niente? No, you just thought, oh, this cotto is very good. No, the coffee was good, by the way. Yeah? No? Yeah. And no, nobody. So there was nothing that kind of captured your attention in the first part, in the first hour and something. Oh, come on, I don't believe you. Something has to. Andrea. Okay, that one is very good. The factorization part. Why?
That's what helps you to produce another part. That's sort of the point to
yeah, I agree. The whole point, I agree with you. The whole point of the first part is probably that one has conditional independence. So the conditional independence helps you to reduce the complexity of the problem. Whatever the problem is. If you think about the likelihood, the best one, right? The first assumption that you make is independence. Why? Because you want to factorize the joint distribution, which we call it likelihood because you invert parameters and the observation, of course, is the parameter given the observation. But it's there, right? And why you do that? Because otherwise you don't have this problem. Oh my God, and what can I do now? To have to go to multivariate stuff? Well, I don't want to go there. Okay, here is multivariate, by the way. We cannot escape, right? But we can reduce the complexity of the problem. Okay, that's a good point. The other one, did the examples convince you or not? Did the example help you to reason about conditional independence, or they didn't have any effect on you? The alarm, the earthquake, the burglary, Mary and John, are they there, or they are just disappeared after a coffee break? There, okay, so there is something. in the first part that we studied. It seems there is few things, but there are a lot. Okay? Now, we are going to study all this stuff in an hour or something, because I want to give you some R code, finally, okay, some practical example. So we have, again, another motivating example. We change the example. We build, okay, from the conditional probability tables, we build our first Bayesian network. Good. We define and represent a Bayesian network, and we learn a Bayesian network from the data. Okay, this is the overview of the second part. And we start with an example in which you have actually two variables. So we reduce the number of variables. This is even simpler, right? So we have a company that wants to hire intelligent people, okay? And they measure intelligence through a test, which is called SAT test. I don't know whether you have done this SAT test, but it's a test to measure intelligence. Intelligence is a difficult concept to measure, right? So here we simplify a lot. We have that you can be high intelligent or low intelligent, and then you can have a nice score in the SAT test, or you can have a low score. Okay? Good. What kind of, let's say, connection in a Bayesian dark sense can we make between these two variables? Are they independent? Let's start from here. No, right? Why they are not independent? Because, well, I expect if the subtest measure intelligence, it should give me some information about the intelligence, right? Now, what is the direction of the arrow? There is an arrow between intelligence and subtest. What is the direction there? From intelligent to sub? Enrico says so. Agree? And there is a, yeah, me too. Choose. So you are intelligent, then your sub score is going to be high, right? If not, it's more likely. It can be that you are like kind of test, and then there is a hidden variable that calls something else, right? So we can add variables there. Okay, but for the moment, let's look about this. This is the table we were talking about. Here we have two variables with which are binary. So we have 2 to the power of 2, so we have 4 probabilities, right? And these are the joint probabilities that you need to specify. This is just an example, so I made up these probabilities. It's not that I calculated it. Okay? And then I kind of write the joint distribution as probability of intelligence times probability of subscore given intelligence. Agree with this? So conditionally on the intelligence, you have higher or lower score, it depends on the intelligence, times the probability of intelligence. This, what I did here is just applying what? The chain rule that we saw before, right? This is true always. Did I reduce these numbers? No. I just wrote the problem in a different way, which is more understandable, by the way, right? If I write like this, it's better than this. I understand better this one than this one. What about you? Is it true? So I understand better this one than this one. Can you comment on these tables? So these are, this table here is the probability of intelligence. And this one is conditional probability table of intelligent subscore given intelligent. Can you comment on this? Or put in another way, is it something that you would assume as probabilities? Or is kind of something that you don't like, and why? Can we do that? No. So how we comment this? So if I'm not intelligent, I have low intelligence, what is the probability of having a nice score in SAT? 0.05. Okay. If I'm intelligent, okay, high intelligent, what is the probability of having a nice score in SAT? 0.8, right? Okay, now the question, is it something that you like as a table, or it's something that you wouldn't apply, let's say, take as good table? It is reasonable for you. Could be, yeah. Oh, of course, it's something that I tell you, it's not 1-1. I'm intelligent, so I will score 1 in the. It's like I'm intelligent. I go to the exam, right? I take 30 and come out always. It's not like that. Get 28, 27, 29 when the professor is not very nice, right? Is it true? It's not that it's always the maximum that you can reach. There is a probability that you reach a bit less. Okay. Now, we have another variable, which is grade. Okay, the grade is a grade in a subject. Okay, you take a course, you score A, B, C, and these A, B, C are given by G1, G2, and G3. Yes. How many entries we have now? So the table that we saw before now is not sufficient because we have one variable more. This one variable has 3 categories, G1, G2, and G3. So we have to multiply 3 by 4. So we have 12 probability to specify. Okay. Now, the grade, how do we relate the grade to intelligence and SAT? Where would you put this in a graph? Enrico, vai. Go. SAT and grade are both determined by intelligence. Okay. Now the direction. Don't worry. Right. So I will go back. So this one here is the graph that I built, right? Intelligence determine who's your grade and your SAT score. Now the question, grade and SAT are conditionally independent, but marginally dependent. It's the same if you think about before, it's the same as before, because if I remove intelligence, but I'm intelligent, then I have more probability to have this high, right? It's the same. Okay. This table here is the last table that we need And it represents what? It represents the arrow, let's say, between intelligence and grade. Yes, okay. And these are conditional probability, right? So this is this link here, and you condition on intelligence, and you have probability of grade. So, okay, so you have to read like this way. Okay, so if you have low intelligence, you take a grade which is low. This is a C. G3 is a C, so it's low grade. If you are intelligent, then you have high chance of taking a good score. Okay. Okay, last thing is we add something more because we want something complex. Okay, and we add another variable, which is difficulty of the course. Okay, if the course is difficult, it's going to be another story. Even if you are intelligent, then the probability that you take a nice score, if the course is difficult, is lower, right? Because the difficulty of the course you have to put there. And then the other one is a recommendation letter. So there is a professor that writes a recommendation letter that is positive or negative, and this recommendation letter will depend on your grade. Okay, so you said, okay, if you grade A, if your grade is A, I'm going to write a good recommendation letter, or always, not always, because other reasons, but often, okay? And this way, okay, this is the way to represent a Bayesian network with conditional probability tables. Okay, what can you observe there? Let's try to interpret it now. Let's look at it. Okay, so these two, these are the simpler, right? Laura, why?
Because they are required to be
So they are like the probability of a course being difficult is 0.6, and the probability of a course being, sorry, it's the contrary. This is easy and difficult. It's 0 is easy and 0.604. So it's a bit more likely that a course is easy than it is difficult. Okay, and this is the same. The probability that you have a subject that is intelligent, as high intelligence is 0.3, maybe too much, but okay. Let's say that we are in a good course, and 0.7 if it's if you have low intelligence. Okay. So let's interpret this one here. How do we build this table? Which is this one here, by the way. Should we start with SAT? This is simple. So the SAT has one parent, which is intelligence. We saw it before, right? So this table we have already connected, right? If you are intelligent, it's more likely that you have probability 0.8 that you take a SAT score that is high, or the contrary was 0.95, right? Agree? Okay, this one here. Why there are all these numbers here? Yes, right, love. Thank you. Okay, so we have two piles, right? So we need to consider on the right part of the formula, so it's probability of grade conditionally on difficult and intelligence. And difficult and intelligence can take value 0, 1, both. So you have to do all the combination, right? And then you have these possibilities. So you have to read this by row. So it's 0, 0, so low, low, and then you have the three scores, three grades, A, B, and C, and so on. So, do you like this table? Are you able to comment this on this table, or is it difficult for you? Potete parlare? Yeah? Sì. It's interpretable, okay. Oh, okay, interpret.
Yeah, the various combination of
Uh-huh. Pick one.
like the third one, which is like high intelligence and low difficulty.
This one.
Yeah. So if one is intelligence and then some is easy, and the grades actually coming fine. That's it.
So you see here, I took the one that it attracts your attention, right? The course is easy. You are intelligent, so the probability that you take an A is 0.9. The course is complicated, T1. You are intelligent, but the probability of taking an A is 0.5. Sounds good? No? Why? Why do you do why? It's okay, you can talk. I put this probability, so it's my fault anyway. We are assuming it's not an appending because it's 0.5. You say by chance you take an A or C. Well, but it's like you add information on. Let's put in another way. I don't know. It's like you have to run somehow. You have to run, right? But you know that when you run, you are good in doing 200 meters, but you are very bad in doing 2,000 meters because in the long distance you are not good. So if I don't give you the information about the running, okay, you say, okay, the probability that I do good in this running is, I don't know, 0. But then I tell you, it's a long run, and you know you are not good in it. Yeah? So this probability is going to be lower because I add this information. And here is the same. Okay, so you have to read carefully this probability. That's my suggestion, okay, even if it looks simple. Okay, the letter, did it catch your attention, Andrea? Can you see it, or I will try to? It's okay? Yeah. So also this one, the professor writes this recommendation letter based on the grade, right? And sometimes it's like, it's not very good professor because it's 0.99, even though you did very well. So you get really angry. Okay, I was really good. And it didn't give me a good recommendation letter. That's the, but sometimes it can happen because he has a lot of students, so I get kind of annoyed about it, I guess. Okay, that's it. Okay, what do we do with this? Why did we build all of this? Why? Because we want to reconstruct the joint probability distribution. Can we do that? Yes. Per quello che, for what Andrea said. for factorization. We know that the graph factorizes according to this probability. Okay, so if we have these probabilities, then we can go back to the joint probability distribution. This is what we are going to do in R. Okay, let's see if I have it. So before going to R, okay, this one. Look at this one. So this is telling you how to build the joint probability distribution giving the tables we saw before, right? Because do you remember the graph? More or less. So we have intelligence, difficulty, grade given intelligence and difficulty, sub-score given intelligence, and letter given grade. Okay? We have all this information, yes or no? Yes. For example, if I want to obtain the joint probability distribution of this combination here, what is this combination? Can you read this combination? Very good. What does it mean, this combination here? Voleva in corso, no, è scappata. Okay, this combination here is the joint probability. Più forte non so. Difficulty of the course. Yeah. Yeah. Okay, and this is the probability. And where do we got these numbers? By this one and taking the right numbers here inside. Okay, you can check that. Is it clear? So this means that, in other words, if you have the structure of the graph, okay, and you have the tables that connect the structure of this graph with the graph, you can recover the joint probability distributions. And from this probability, we said everything. We can recover everything. Okay? Is it okay? So this is the exercise I want to show you now. So now we are going to start from this one. So if you don't have, you put in a paper so that you will have visualize it there. From this one to recover the joint probability distribution. Okay? Questions? No? Okay. Yes. And there are no stupid questions, just stupid answers. Yeah. Bayesian network?
Yeah. Network, but I mean, why Bayesian?
Because it's based on Bayes rule.
Okay.
The Bayes theorem, okay, is inside. So there is nothing to do with prior probability.
Yeah, okay.
That's the question.
Yeah.
It's not a stupid question because everybody gets confused about Bayesian network with Bayesian models. Okay, this is not a Bayesian. It has nothing to do with Bayesian. I'm not talking about prior probability, even though there are prior probabilities. Right? I'm not assigning prior people, but I'm using yes, but that's a prior probability on intelligence, for example, right? I'm using the Bayesian theorem there. So Bayesian network comes from there. Yeah? Yeah, it's a good question. Okay. Okay. Can you see the code? Yeah, code. Is it okay like this? Is it okay? Yeah. So you will find this code in the material of the course. So don't worry, I will give you the password at the end, so you don't have to copy this. It's just understand the steps that are there. So just look at the code and that's it. We said that you are familiar. I'm assuming you are familiar with R. I'm not going to explain R. So this first bit here, it tells you, well, the first one is just clean my console because you never know what is there. And then the second step is load the necessary libraries. So if you don't have installed in your laptop, after all, you can install it. Please do it in the break time so you don't waste time at the end. grain, BNLearn, iGraph. This is VCD extra. We will need for doing some nice plot on the conditional probabilities. And well, the last one, gplot, is a function that I made. You will find it in the materials, okay? So it's just to plot. Okay. So the variables that you have are this. Let's repeat it. Difficulty of the course, intelligence, grade, SAT, score, and letter. Do you all remember these variables? Yes, okay. These variables have some levels, okay? They are almost all dichotomous, but we have this grade that is A, B, C, right? We say that these are G1 is A, G2 is B, and G3 is C, yes? So these are the levels of the variables. Now, what we are doing here in this step is to build, so the function to build the conditional probability table is CPT table. Okay, so it's CPT table, and then there you have to put the nodes, the node you are considering conditionally on what? On the parents, right? So difficulty, for example, do you remember it was on the top of our Bayesian network, right? So it was without any parents, yes? And I put it here. These values are the probabilities assigned to what? The levels of the variable. So the first one, 0.6, is D0. So it's low difficult. The second one, which is D1, is high difficult, which is 0.4. Yes? Okay, that's the first, and I'm not going to comment the second table because it's the same as before, right? Because intelligence, we said it's without any parents, blah, blah. Okay, that's it. Okay, let's go to SAT. SAT. The SAT score was related to intelligence, right? So we have two conditions. There is a filter SAT conditionally on intelligence. Now, how many values of probabilities we need? 4. Was coffee or not? There was coffee, right? How many values? 4. 4 values, right? Okay. What are these 4 values? What are these 4 values? They can be joint, marginal, or conditional probabilities. Conditional. Oh, yeah, man. Conditional probabilities, right? Okay. Good. So it was 0.95 and 0.05. Do you remember? We commented it, right? Okay. So let's visualize it. Looks something like this. Okay. In the plot, in the graph, was better, but it means the same. And now we have letter. Well, okay. And grade. Okay. So all this first part was done to build what? The conditional probability tables of the Bayesian network. Okay? Now, what we want to do, we want to recover the joint probability. Okay? And okay, we have two ways to do it. Doing by calculation by hand, we don't want to do that, or using a function in R, which is called compiled CPT. Okay, this function does what we want. So it builds all the probability, the joint one. Okay. Okay, let's see whether. Okay, so I will explain in a moment. Just want to show you this one. Okay. You see the plot? No, because the screen is not shared. Okay. Okay. So we have this plot here. So it's, I use compile and then the Girain function to transform the conditional probability table in a directed graph, directed one, and then I use TK plot. I will show the code right to build this one. This is very nice because this is interactive plot, so you can move the nodes as you want. Okay, then you can take the coordinates of these nodes and plot in another graph. Okay, so this is nice because you organize your variables according on how you feel you have to show this plot, right? Usually what you do is from the top, right, you try to go down with the arrow, always following the arrows. Yes? Okay, so this means in this way, do you like in this way? No, I guess no. Right? Because we want on the top don't remember, it was like this in the contrary, but this doesn't really matter. Okay. Like this is a bit better. Yes. Okay, so you have intelligence difficulty, intelligence, let's cause SAT, difficulty graded, these are related, and you have the also letter. Okay, good. Let's go back to the code. Okay. Oops. Okay, so in order to do this, I use the function grain on the conditional probability table, and actually that one is the joint probability table. The CPTS object is from compile, you see that, and that one we say this is the joint, and then you build the DAG from that one. Okay, so it's inside the object Bn, which I created. You have the object DAG, you recall it, and in order to visualize it in TK plot, you need that the object is an iGraph object. So because TK plot is a package that is in iGraph, so it wants a graph, a directed graph, which is iGraph object. Okay, and so this is what I did. With vertex.color is just something fancy to visualize the nodes in light blue. Okay, you can put whatever color you want. You can even color the nodes in a different way. Okay, good. Then you can use. Okay. TK chords. This one here, it gives you the coordinates of the nodes. Okay, it's like you are fixing up the nodes. And now you represent, okay. Something like this. Yeah, and you can play with colors, measure of the links, the arrows, measure of the names of the nodes, and all this stuff. It's inside the function gplot. You are going to play a little bit later on. Okay. Good. Last couple of things in this example. So we started from a Bayesian network with conditional probability tables. We built the joint probability. And now we want to answer some query. Okay, do you remember the query, the questions? For example, I want to answer a question on letter and grade. Let's say I get an high grade. What is the probability of getting a good letter, for example? Okay. To do this, first you have to compile and propagate the graph. This concept, I'm going to give something about this concept, but you need to study a little bit more about that, okay? But we are going to talk a little bit. For now, it's just, for you is propagation. Propagation means that you have a node, right? You fix something on this node, and this node propagate is evidence on the network. Intuitively, it's easy. Practically, it's a bit more difficult. Okay. So, what are these? So, this function here is called the query grain, and it can answer different questions. It can answer questions on posterior probability tables. Now I'm going to tell you why posterior. Okay, marginal. So on this node, give me the marginal probability. Given what? Given the graph that I gave you. Right? These probabilities are based on our assumptions, on our conditional independence assumption. Yes? Conditional independence or joint. Okay, and all of this depends on what you put here. So if you put marginal, it's going to give you marginal probabilities. If you put conditional, it's going to give you conditional probabilities, or if you put joint, it's going to give you a table of joint probabilities. On what? On the variables you put here. Okay, for example, this square here is going to give you the marginal probability distribution of the node difficulty. Do we know this one? Yes, because we have seen it, right? How many probabilities are there? 2. Okay. This one is going to be a bit different because it's going to give you the conditional probability of the first node that you put, so in this case, letter, given grade. But if you put another variable, it's going to be letter given grade and the other one. If you're going to put another variable, so it's always like you have to read this conditional as the first node that you give, conditionally on all the rest that you put there. Okay? For example, this one. Now, so you see this this probability of letter given grade. Do you remember the graph, right? It's going to be grade is the parent of letter, and now we are asking what is the probability of having a good letter given the grade? So these are the probabilities. Right? Now the question is, suppose that I condition on intelligence as well. So I condition letter with grade and intelligence. Do you remember the graph? Yes. Shall I show you again? The graph. Do you remember it? Yes. Okay. Do you think our belief on the letter should change or not? Yes.
For me, no.
For you, no. Okay. Why?
Because the letter is just based on what grade you take. So given the grade, the letter is conditional.
And they are. Do you believe it's like this? The explanation is this because, okay, the answer is correct. The explanation less. Agree or not? Or you agree with me? I think so. It's okay. You can have it.
I agree with you.
Yeah.
The grade depends on intelligence, but when we know the grade, intelligence does not have information that we test.
But it's different. It's a bit different. The way you put it's a bit different or not?
Yes.
Okay. So you said for it correctly. He was trying to tell the same, but in a different way. So because the answer to David, right, was okay. Let's remove information about the grade. Okay, I give you information about the grade. Your probability about the letter will change or not? I will show you. So if I remove, if I do this one, letter grade, right? Then I do letter grade intelligence.
It won't change.
It won't change. But let's do it. Right, like this. You see? Our intuition, Davide was right. this, sorry, they are the same. Why? Because adding information, having information on the grade is useless. I don't need it because grade give me all the information. Okay? This is an assumption that was coming from our construction of the Bayesian network. It's not that in reality it's going to be like this. If you calculate this in a data set that you collect, instead of creating from scratch, you will find differences. It may be that these differences are small, but if you don't make the assumption of independence, conditional independence, and parents and stuff like that, it's not going to be like this, right? The other thing was this is different, right? Another stuff. So intelligence is going to give me information on the letter if I remove grade. This is what you correctly said, okay? That's important. So if I have information on grade, I don't need information. But it doesn't mean that the variables doesn't influence. Yes? It's important. Okay? And you can play around. Now, the letter was the node, the final node of our graph, of our log. But we said, can we obtain information on, for example, intelligence, which was above, given the letter? Now it's a bit different, right? It's a bit peculiar because the arrows go down, but we are going to make inference on the top. Is it something that you find strange or it's normal for you? It's normal, right? Why it's normal? Because it's like in a medical diagnosis, you have COVID, right? And you have all the problems that COVID caused you. And then what you observe is not COVID, is the final stuff, right? You have flu, you have fever, you have problem with respiration and stuff like that, okay? And then from this, you go above and you say you have COVID. That's the normal reasoning, actually, right? So now I have the letter, but I don't have information about your intelligence. And now from the letter, I want to recover the intelligence. Can I do that? Yes. Why? Because actually I didn't give you this conditional probability tables, right? Did I? No. I gave you other probability tables, but not this one. I can do it because I have built the joint, right? How do I do that? This in our last step. So we want this probability here. Okay. Can you try to read it? Quando vi la poi.
So if I didn't have a letter, there's 86% probability that I'm not intelligent, 14% that I'm intelligent.
So if the letter is not good, let's say, and the professor gives you a shit letter, let's say, yeah, you have the probability that you are wrong is 0.85, yes.
And the probability that I'm intelligent is 0.14. Whereas if I have a good letter, the probability of being intelligent is 46%.
So it changes from this one, you go to this one. Okay? So and this is going back from the last node to the top. Yes? Okay, you can answer all the queries you want or the queries you are interested in. Che ora è la pausa? 12:30? Ho mezz'ora, giusto? Abbiamo ancora mezz'ora? Yes? Okay, good. Let's go back to the slides. Okay, so far it's okay. So now we are going to talk about the Bayesian. Okay, we kind of understand what is going on, what can we do when we start from the conditional probability tables, we make inference and we. Okay, now we are going to do the contrary. We have data and we want to learn that work. Okay, so it's the contrary that we did so far. But before, I just want to give the definition, formal one, of, first of all, local probabilities in Bayesian network. So you have okay, this you can read on yourself. Okay, this one. So you have this one. This telling you. So you have a Bayesian network structure G, which is a directed acyclic graph. We said, okay, we know what is a directed acyclic graph. We have random variables. Each random variable is related to a node. Okay, it's one correspondence. And then this G encodes a set of conditional independence assumptions, which are known as local assumptions, such that Xi is independent, conditional independent of non-descendants, given the parts. This is what we studied from the example formulated mathematically. Okay, so it's like if you condition on the parts, what is on the top is conditionally independent on what is on the part below, right? But it says not all the roots, but non-descendants. Because if I take the child, right, conditionally on that, it's not independent anymore. So I have to go above the parts to find conditional independence. But if I go below, and we just showed it, right, it's conditional dependent. Yes? So if you think about the example, our example, the last node was, we said the letter, right? Go above the letter was the grade, right? So above the letter, it was intelligence and sub-score, right? So if I take grade conditionally on the parts, and I have something above, this grade is conditionally independent. On what? On SAT and intelligence. But it's not conditionally independent on the letter. Because it's a descendant, okay? It's a child of the grade. Yes? This is what this formulation is telling you. Okay? Okay, now this formulation gives you the opportunity to use the factorization. What is the factorization? Now we know what is the factorization because we learn it by samples actually. So the factorization tells you that if I have a graph, so I have a DAG, I have a set of conditional independence, local conditional independence, and then I can write the joint probability distributions as a product of each random variables given its parts. So I can factorize this joint distribution according to this formula. And that's the basic. This is the core of all the Bayesian network, let's say. Is it clear? Okay.
It's something related to like Markov properties.
Yes, it is something related to Markov properties, which we are going to see in a minute. Okay, so what kind of Markov properties or conditional independence can we read from the graph? It depends on which kind of relations we have. So we can have this, let's say, 4 kind of relations. A chain, X, Z, Y, okay, or this chain is a bit different, but it's a chain. C is a common cause, the one that we saw before, okay? And this one is a V structure. This is called a V structure, okay? These 3, if you use factorization that we saw before, encodes the same factorization of the probabilities. So you can actually not distinguish between this, and this. They are the same in terms of probability, in terms of likelihood, let's say. Okay? Instead, this one is different because it encodes a different set of conditional probabilities. Do you remember which is the difference between this one and this one? Yes, very good. We saw that, right? It's the exactly. So, okay, so here we talk about direct condition. So if there is an arrow, then they are dependent. You cannot do anything to remove this dependence, right? Oops. So if this one is a common cause, then as we said, X and Y are independent given Z, marginally independent, and then we have, this is called the common effect of collider of this structure, and it's X and Y that points to Z, and are independent unless Z is sub Z and marginally. Okay, this is what we said and recon with you and so far. Okay, so these are the structure. Where this goes to separation. Actually, this is called deseparation. So this is because directed a secret graph. Separation because it's something that conditionally only separated to stuff. Okay, this is the definition. So we said that 2 nodes or 2 sets of nodes are deseparated if. So if we have a node V, which is not in the set C, which is what separates, let's say, A from B, or if B is not collider on the path. Okay. This seems like difficult, but if you think, so if you have Z, X, and Y, okay, and this Z is what you condition on, right? This is a collider, so you don't have the deseparation, right? But if this one, this z becomes p, and z is above, then if you condition on z, okay, these are independent because there is no more any more collider information. This is the first bit here. Okay, this v shouldn't, must not be in the set C if you want the separation between x and y. If it is in the set C, okay, then it's like you are giving information. The large sums. You cannot give that information. Should be above. Yes? Or if you have the other structures, then it's not a problem because you condition on that and then you are deseparated. Yes? Okay, good. This stuff here is just to show you that when we use the factorization, we can see what we said before. Okay, so let's say this is a chain x, z, and y, right? We have a chain. Conditionally on z, what do we expect? That x and y are separated. So they are conditionally independent. It's a chain. Convinced? Yeah? Okay. So we have to prove it. How do we prove it? How do we prove this one? This conditional independence, sorry. So we said that if we write this one, then the conditional joint probability distribution should be written as, must be written as the product of x given z and y given z, right? Okay, so what I did here is, first of all, I took the conditional, I used the chain rule of Bayesian network here. So this is just pz, right? This is given by the factorization property of the Bayesian network. Then you write this bit here, px times pz given z, x as px given z times pz. I'm just doing what in the chain rule we did before, right? Exchange the two, doesn't change anything. Then you have pz and pz. So you remove this one and this one. And then you prove that if these are conditional independent, and you use what? The factorization property, then you can write this probability as the product of these two. Yes, this is just to show that it's true, that the factorization work as we showed the separation. Instead, in the last framework, we have that these two are conditional dependent. This is what Enrico said, because we have a collider, a V structure, right? And in fact, you can write this one as this one. You cannot do anything there. Okay, in all the other cases, you can do that. You can play a little bit with probabilities, you can do that. But in this last case, no. Questions about this? You have time, more or less. Is it clear? Sure? Enrico, you want to go simple plus? No? Va bene? Andrea, a posto? Okay. Good? Yes. Okay, last bit, and then we go to the practical example in R. So just 5 minutes more, it's just structural learning. I think tomorrow Federico is going to talk a little bit more about structural learning. So I'll give you just some hint because we are going to use it, okay? So There are a couple of algorithms or two directions that you can take. One is in constraint-based algorithms. These are all based on conditional independence test. So you test every time if an arrow is present or not, conditional on the rest. Of course, you have to pay attention there. You don't have to create cycles, right, in the graph. And then you have to pay attention to what you move, because we said that there is a particular structure, the width structure, that has conditional dependencies that are different from others. The main algorithm used for this is called the PC algorithm. Okay, this is not what we are going to use, by the way. We are going more in score-based algorithms. This one, I think you are more used to it. Like in the regression model, right? When you do model selection, what you do? You try to add a variable or remove a variable according to a score. What kind of score you use usually? BIC or AC, for example, depends on whether you want the model to have more parameters or less, right? Because AC usually give you more parameters, of course, than BIC. But this is the same. Now, the question is, what does it mean to do model selection in Bayesian network? In regression model, we know. We put or not a beta, and we said that the variable influenced y. Here, what does it mean? What do you think it means? Adding or removing an error. So it means that you adding an error means you add conditional dependence. So a bit more tricky, right? Removing, you are removing a conditional dependence, and it depends on what you remove. Then it's going to be a bit more difficult to interpret. It's not just removing that one, that you remove one conditional dependence. There is more, right? But it's that one. You change the data. You add an edge, you remove an edge. When you add an edge, you add complexity. When you remove an edge, you remove complexity. And every time you try to understand whether your new tag is better than the old one, but you are moving in a space that is big. Because how many graphs, DAG, can you have? So with few variables, it's already a lot. Okay, if you think, because you can play with the arrows also. It goes from A, B, C, or BCA, and stuff like that. So you have a space of models that is much, much bigger than in the regression models. Okay, so you need a heuristic search algorithm to explore the space of graphs as well as you can. Because often you go in a local point and you don't move anymore. And this is what, in particular, hill climbing, scalare la collina, try to do, right? Try to search and move around that to find the best one. Is there a best one? I don't know, but one that is good for your problem. And then you have other algorithms. Okay, I think we have 50 minutes, something maybe more. This is just algorithms for the big score, you know it, to show. Okay. Last thing that I have to tell you is this one. We talk about a discrete Bayesian network. So if you have, for example, a mixed problem where, I don't know, you have 10 variables and three variables of these are continuous. You can always use discretization. Okay? When you use discretization, you are removing information, right? But if you want to use a pure discrete Bayesian network, you need to have all variables discrete on discrete space. So you need to have some cut off on your variable to remove the continuity. And you say, for example, I don't know, age, right? You have child, young, adult people. You create these categories. Of course, there is a selection that you have to make. This can produce stuff on the graph, on the conditional independence. So pay always attention. But we are working on the discrete case. So if you want to work purely on the discrete case, you need to discretize. Sometimes it's good because when you have a continuous and discrete case, in the continuous case, mixing the two is not really easy, and overall there's just one distribution which is called conditional multivariate Gaussian distribution that work on that problem, okay? So sometimes I really prefer to work either on discrete case, all discrete, or if I have all continuous variables, I will work on the continuous case, but not to mix them, yeah? Unless there is really a good reason to do that. This is my advice. And then,
Is it more additional problem or is there other also?
no, it's related to the multivariate distribution assumption that you have to make to let it work. So if you think about a mixed case, right? And you have continuous and discrete. Okay, you can condition on the discrete. So you have all the y that are continuous given the x that are discrete. And this distribution is conditional on the discrete, can be the multivariate Gaussian distribution. But if you go the other way around, then you cannot do everything because you have continuous there on the discrete, okay? So it becomes a problem. So you even have a problem in which direction you can go. But there is of course one distribution of this conditional multivariate Gaussian distribution that work on that. But you have a lot of problems. Even computation. Yes. So you can work in small problems. These are packages I put here in a table. So the yes means they do everything you read it. So discrete continuous case. So this one means that deal. If you want a package that work on the mixed case, you have to look at deal. This package works in continuous case. Then these are the algorithms that works on this kind of structural learning. So constraint score of hybrid. Hybrid mix the constraint and the score. And then, well, we have structure parameter learning. We haven't talked about it, but there are algorithms that does this and approximate difference. Okay, so example. Example R. So okay, this is our example. Now the example, I mean, it's the same as before, in the sense that these are data from the 1, 2, 3, 4, 5 variables that we talked about. Okay, so we have again difficulty, intelligence, sat, grade, and that. This time, I'm not giving you conditional probability tables. I'm giving you the results of a survey on, I don't remember, 2,000 subjects, more or less. Okay, and then I just interview or give them the sat score, the grade, and the letter. And I said, okay, the first subject took a difficult course, has low intelligence, has a sat score of low, grade B, and the letter was negative on this subject. Clear? So this is your data set now. What do I want to do with this? What would you like? So what would you do without graphical models? Nothing. No. A huge that you cannot even read, right? Because it's like if new frequencies, you cannot really read something, right? Yes, it's a really huge contingency table.
I will be able to describe that this table probably.
With this dimension?
Probably
okay.
My target is the joint.
But the joint distribution is not going to simplify your problem, right? So you have to, okay, now there is, let's put it this way. Somebody gave you this problem, the company, you remember? The company at the beginning wants to hire a statistician and say, okay, let's solve this problem together. And then I hire you if you solve this problem, otherwise no. Okay? And then you give them the contingency table. Do you think they are you? No, right? Because you are not giving anything. They want to hire based on which kind of information? Intelligence, right? So would it be good to use some log linear model to understand what intelligence is related to, what are the conditional independence or not? Yeah, you could do that, but we are now in a course of graphical models, so we want to create and give them what? The Bayesian network. We want to give them that. Because with nodes and arrows, we can explain what is behind this. And then we can answer their queries with probabilities that they will understand. But marginal, but not on all of that. If they ask you a particular query, then you will answer. But always kind of conditioning on something, right? Not on all the variables, because you know that you don't need anyway. So I want to kind of, first of all, learn the graph, right? How do I learn the graph? We said that we use the high climbing algorithm. So the function is in the package Bayesian network learning, so BRN learn. The function is H, I, C climbing. Then you have to give the data. So this must be a data frame or a contingency table, because then it works with contingency tables. And then you have these two perturbers, their start, they help us to not stop in a local high score. Okay, help us to explore more the kind of space of graph that we said it's huge. Yes? Okay. So the score we use is PIC. With PIC we penalize more, right? The number of edges that we have. Okay. So this is quite fast. You see? Has already done everything. And then we can maybe this. Can you see now? Okay. You like it? Okay, shall I put it in a different way? Because in this way you can notice. This one was the old one. Okay. But this one here, I didn't tell anything about conditional independence. I use the high climbing algorithm to search the model space. So it went from an empty graph, completely empty graph. They start to see, okay, let's see the score of the first graph, adding some edge for one node with others. Okay, the score is better, let's go on, and so on. So he explored this space, and he gave me this one. Does it look familiar or not? It's exactly that one, right? So exactly that one. So now I can tell you, I simulated the data from the Bayesian network. And it's not, so these are not real data, these are simulated data from the network. And I recover exactly the network from which I simulated from, okay? So this means that, at least in this case, it gives me a good results, okay? So now let's suppose that one arrow was in the wrong direction. Let's say that this goes from intelligence to grade, and this from grade to difficulty. So this arrow was inverted. Is it a different network? So I put, let's do this one. This, okay, like this, and I will do this one here on the other way around. So I have common both, but now I have a chain. Is this a different network? So from here, you will go from here to here. They are marked equivalent. Exactly. They are marked equivalent. So you cannot really distinguish. Instead, if I look at this one, this is a big structure. And I put this arrow goes from greater to difficulty, then I will change the conditional independence. Right? Because I have a chain now which has conditional independence which are completely different from the opposite, actually, from the V structure. So when you find something strange, for example, I don't know, let's say that this arrow goes from greater to intelligence, you can create what is called black list and white list, But when you do that, you have to pay attention to the conditional independence that are behind the plot, okay? Because in that way you say, okay, look, I don't want the age from intelligence to grade because I know that it goes the other way around. It goes from grade to intelligence. In this case, it's not true, but let's suppose it's like that. So I will put a constraint on the arrow that goes from intelligence to grade. This is the. Sorry, I will waste kind of 5 minutes just to give you the concepts and then we go. Okay, so this is called blacklist. As is this part of the code here. So you kind of create a matrix, okay, square matrix, in which from row and columns you have the names of your nodes, variables, and you put 1 from 2, okay, when you don't want the arrows goes from here to here. For example, here, okay, this is the black matrix, the black matrix is something like this. You see, it's all 0 right now. So now I want to create a blacklist between 3, SAT, and intelligence. So it means that I don't want an arrow that goes from SAT to intelligence, because I know that it's the other way around. Okay, I put 1. I create this, that is the blacklist. So I don't want an arrow from SAT to intelligence. Okay, this is what it is telling. And I put this constraint in the high climbing algorithm, and it knows it must not estimate this arrow. If you want, if the algorithm wants, it can invert the arrow, but not this way. Okay, doesn't change anything, and the plot is that one. On the same way, you can create a whitelist. So the idea doesn't change. So you build a matrix, square matrix, and you put 1 when the arrows must be present. So you want an arrow this time because you know there is this connection, and you want that conditional dependence between these two. I want that. So I will put here from to, okay, the 1. For example, from grade to letter, I know that there will be an age. I will add the algorithm, okay, with the whitelist, and you can run it. You want to take the break and we finish the last part of it doesn't matter. Should we take the break? Because it's time, and then we finish this last part with queries, which I've already done, and then we start with the last part of the course. Yes? Yeah? Okay, let's do it.